Hi, so today we're going to learn about chaos. So what are we going to cover in this video? We're going to first start with an overview of chaos, show you what most people think of here, the Lorentz butterfly. I'm going to give you an introduction to chaos. I'm also then going to introduce you to the Henon map. I show you the Lorentz butterfly because it is what most people think of, and kind of the base of where the Henon map came from. I'm going to show you some map basics, the iterates of the map, the graph, how to manipulate it, some fixed and periodic points, what those have to do with things. We're going to give you a formal definition of chaos and explore the three main aspects of it. So what is the Henon map? The Henon map is a simple two-dimensional invertible iterated map with quadratic linearity and chaotic solutions called strange attractors. So these are the two formulas. You have x, n plus 1 equals yn plus 1 minus alpha, x n squared, and yn plus 1 equals beta times xn. So alpha and beta are our two parameters. For this graph, alpha is 1.4, beta is 0.3. Those are your basic, what everyone generally uses to study the Henon map because they are known to have chaotic solutions. For my study of the Henon map, I looked only at alpha and beta greater than 0. When beta is 0, the Henon map reduces to a quadratic map. And when alpha is 0, it's a one-dimensional logistics map, which you can see just by plugging them in to the equations. So what I'm first going to show you is just some basic iterates of the Henon map. So in Excel, I set my first column equal to n, the number of iterate. Second column, x sub n and y sub n. So my initial conditions are both x sub n and y sub n are equal to 0. I set alpha equal to 1.4 and beta equal to 0.3. And what I did for alpha and beta is I set up a counter in order to be able to switch and change the parameters easily while still visualizing it on this graph here. So for x sub n, I simply plugged in the formula into Excel like you would for any other formula. It is yn, so c2 plus 1 minus d2, I always want to take this one, times xn squared. And then you just simply drag it down to as many iterates as you want. I did a whole lot of iterates so I could get a nice looking graph. And then I did the same thing for yn. I dragged it all the way down. So you can see here, with some basic iterates, this is what your map will look like. This is what the basic Henon map looks like when people study it. And if we move alpha to 0, we can see how the graph changes as alpha increases. We got some periodic points. As alpha gets up to 0.854, we have some periodic points again, and back up to 1.4. I feel like this is a lot easier to see when we graph n versus xn and n versus yn. So these graphs here are just your xn and yn values. You can see down here that we quickly go to an equilibrium. Still just simply going to an equilibrium. Here we get a little bit of wave, but we still go to that equilibrium. Here you can see we start to get some periodic points. Period 2 it looks like. Here's some pretty looking not periodic, but maybe there might be a little bit. But then that's just alpha. So next we're going to talk about the specifics that you see here of the periodic and the fixed points in terms of alpha and beta. Okay, so now we're going to start going through kind of how I solved for this map. So you can see here again I just wrote down the formulas with my initial conditions and my parameters. I have the first couple iterates in here just so you could see how they were done by hand. And again, note that when beta is 0, the Henon map reduces to a quadratic, and when alpha is 0, it is a one-dimensional logistics map. So, a fixed point. So the formal definition of a fixed point is that the point x is a fixed point of f of x if f of x equals x. So how did I do this? I used matrices to find these, and I just set xn plus 1 equal to xn and yn plus 1 equal to yn. So what I did was I solved for x using the quadratic formula and got this formula here, of course when alpha is not 0. And then what I ended up finding when you solve for this, I'll show you here, is when alpha is less than -1/4, 1 minus beta squared, everything diverges to infinity. So if beta is positive and alpha is less than this, everything will diverge. When alpha is between -1/4, 1 minus beta squared, and 3/4, 1 minus beta squared, what you get is 2 fixed points. And I'll show you these on a graph in Excel or Mathematica in a minute. But what you get is 2 fixed points. And then when alpha is greater than 3/4, 1 minus beta squared, this is where you start to get periodic points and things begin to be chaotic. So to sum that up again, is when alpha is less than 1, you have fixed points that appear that are periodic. When it's greater than 1, you have no fixed points. You start to get periodic points, chaotic points, and so it appears that alpha is much more sensitive than beta. So what I want to show you real quick is using the Excel sheet that I used in the beginning, an n versus yn graph and an n versus xn graph. I'm going to use these to show you what I just showed you mathematically with the fixed and periodic points, how that looks graphically. I have 2 scroll bars up here, one for alpha, one for beta. All they do is enable me to change the parameters slightly, either or, to show you how these graphs work. So right now what I'm doing is just moving alpha, increasing alpha by about 1/10 or 100th every time. And you can see, obviously yn is not affected because the equation relies on beta, but you can see how xn begins to wobble, but then it very, very quickly moves to an equilibrium. So we continue to increase alpha. We'll see a little bit of more wobble, but you can see down here that it still will eventually go to an equilibrium. We only have the first 200 iterates in both of these graphs. Here, about here, when alpha is 0.756, you can see we start to get a little bit of periodic fixed points, and then you can see that that becomes more clear as alpha increases. And here, because beta is 0, this will always be periodic. So we'll move alpha back. Now we just look at y. Again, we move alpha. We move beta some. And you can see how the graphs change. What's neat about these graphs is, although their equations are different, their graphs seem to mimic almost perfectly each other. So you can see as x becomes periodic and a little wobbly, so does y. So I'm going to set beta. I'm going to move alpha back to 0, set beta to 0.3, which we know eventually will give us chaotic points. And now we're just going to evaluate alpha as we move it. So you can see here, again, they mimic perfectly. Here we get some beautiful mimicking wobbles, some periodic points. Here it's very periodic, you can see that. Again, fixed periodic points. Now you see we start to get a little bit of inconsistency up front. For the most part, still the same. Again, a little bit of inconsistency, but the same pattern throughout the rest. And let's see where this actually begins. Okay. So I would say between 1.078 and 1.092, you can see it really start. Here we still got a little bit of pattern though. And then as alpha gets close to 1.3, you can see, which is what we know has chaotic attractors, you can see how it goes from chaos, has a little bit of periodic fixed point again, and then moves back to chaos. So that's just how you can see it graphically by manipulating the parameters. So what I want to do now is define chaos formally. So Devaney's definition of chaos says, let V be a set where G from V to V is said to be chaotic on V if 1. G has sensitive dependence on initial conditions, 2. G is topologically transitive, and 3. The periodic points under G are dense in V. So what I have here is the Lorentz butterfly, which is really simple to use when defining chaos because it's really easy to see each section. So the first one is sensitive dependence. So the definition of sensitive dependence on initial condition is G from J to J has a property that for each x in J and any neighborhood n of x, there exists a y in n and an n greater than 0 and s greater than 0, such that the absolute value of gnx minus fny is greater than sigma. So basically what that says is that as 2 points start close together in the same area, eventually they'll diverge. And you can see that already happening in the Lorentz butterfly. These points started in nearly the same spot, and as you see, they start to diverge and get very further and further apart. The second part of that is topologically transitive. The definition of topologically transitive is that A from J to J is said to be topologically transitive if for any pair of open sets U and V in J, there exists a K such that G of K of U intersected with V is not the null set. And what that basically says is there will be some iterate of G in the open set U intersected with an open set V. It will intersect the open set V. So as you can see here, that almost goes along with the periodic points being dense. What it means is that at some point, these points will intersect every part of the graph, regardless of where you put that open set. So I could put an open set over here, and eventually these points are going to fill that set. You can see here that the red one already starts to get a little closer, and eventually there will be a point inside here that hits this graph. Probably that green one. So that's the formal definition of chaos and the Lorentz butterfly used to model it. So what I want to do in my last few minutes is show you the 0-1 test for chaos and how I use that to find chaos in the Henon map. So because the Henon map was two-dimensional, it was a little difficult for me to use the traditional methods that I'd use for like the logistics map to find chaos. So this is the paper I used. I'm not going to go through it all, it's like 27 pages. But I want to point out a few things about the 0-1 test. So what this really does is it distinguishes between regular and chaotic dynamics. It's used a lot for things that are not one-dimensional. Stuff like ordinary differential equations and recursion equations. So what this does is it inputs a one-dimensional time series to drive a two-dimensional system. Here we see P and Q. And then we define the mean squared displacement m of n and its growth rate, which is k, which is the limit of the log of m of n over the log of n. So that's how the test works. To summarize it, what we're going to look at is what you'll see is if you get a value close to 0, it's bounded and has regular dynamics. Close to 1, it's going to be chaotic. And then this is what it will generally look like. This is P plotted against Q. You see here that this looks normal, like a normal circle. It's a logistics map. And on the right over here we have a chaotic map. So let me show you. Here, this is using the Henon map. I have my beta set at 0.2, alpha 0.74, x naught 0.09, and y naught 0. So what you have here is the same thing, P against Q. You can see it looks like a circle. Very regular. What we did over here was we calculated K, and we calculated the log of the m of n. So right here you can see that we have a value very close to 0 for K. So we have regular dynamics, and this is what it ends up looking like. And then in the other one, this is for betas 0.3 and alphas 0.14, which we know have chaos. You can see here P and Q, this is very chaotic. it looks nothing like anything you would expect. And here we have a k-value of 0.69, very different from 0.04. So this just shows using a different test that kind of takes a two-dimensional system and uses a one-dimensional time series to show that the Henon map is chaotic.